Okay, sorry about that. It got disconnected. But anyways, we just started the question, so we'll start from again. The first question, and one second. Okay, so it got disconnected. So let's start again. So we started on the first question that we have two dipoles and they are perpendicular to each other, each having a dipole moment of P. We have to find out the net dipole moment. So we were discussing that the total dipole moment is the vector sum of individual dipole moments. Okay, that was our basic. Okay. Or we can say it does not depend upon their separation. Okay. And in this case, the magnitude is given as P and they are perpendicular to each other. Okay. So let us assume that we have this as P1 and it is in x direction, and this is our P2 which is also P but in y direction. Okay. And therefore we can say that we have a P1 that is in our x direction and P2 that is in y direction. Therefore our resultant dipole moment let us suppose that is our P net will be equal to P1 plus P2, or in terms of magnitude we can write our P net will be equal to our P1 square and P2 square, and individually both are equal to P. So this will be coming as our P square root of 2. Okay. So this was quite straightforward. Okay. Next question. It states that two parallel discs each have radius r and are separated by a distance. Okay, a distance is L. The surface charge densities are sigma and minus sigma. What is the electric field at a large distance r along the axis of the disc? Okay, so we are given two discs and the distance separation between them is given as L. So this is suppose our disc number 1 and this is our disc number 2, and we have to find out on the axis of disc. Suppose this is the axis of the disc, common axis, and the distance between them is given to us as our L, and we have to find out the electric field. And this electric field is, let us suppose, our point P, and that is our at a distance r along the axis of the disc. But in this case okay, and we are also given that the disc are having a radius r and the charge density is our plus and minus. And important part is that the distance between the point P and the disc is very large. Okay, therefore we can say that our at large distance that is our r is very much larger than our both radius as well as the distance between the discs. Therefore these oppositely charged discs can be treated as, or we can say they are going to behave like an electric dipole. Therefore you can say the opposite charged disks behaves like an electric dipole. Therefore, we are going to find out the dipole moment of the system at point P. Dipole moment of the system. And the dipole moment of system, for that we need to find out the charge, except the, you can say, the opposite, the charge density is same. Okay? One is positive, other one is negative, but the charge density is given to us is same. Therefore, we can write that each charge on each disk let us suppose that is our Q, and then this Q will be equal to sigma bar I square. And based on this, the distance between these two disks is given as L, and like I said, these disks can be treated as like a dipole. Therefore, we can write the formula for the dipole moment, and the distance between these two is L. So from here, you can say that the dipole moment, let us suppose that is our P, and that will be equal to charge multiplied by the distance between the two. So we simply substitute value of charge, so we get pi r square times L. Now we can use the basic formula, that is our electric field on the axis when the point is very far. So we can say the far field, electric field on the axis. Far field electric field on the axis. And here we are going to write the electric field formula with respect to the dipole. Okay. So you can say for the dipole, the electric field, the field on the axis at a large distance r. And we can write this as electric field on the axis will be equal to 1 upon 4 pi epsilon naught twice the dipole moment and the distance cube. We can easily substitute value of P, so we get the electric field at a point r, at a distance r rather, will be equal to 1 upon 4 pi epsilon naught, and this is our twice, it comes as our sigma pi r square L upon r cube. And so in this case we are given the condition that the value of r is that the distance is much larger, the radius of a disk as well as the distance between the disks. Okay. So we can say sort it out. This pi goes by pi, this goes by 2, and therefore this can be approximately equal to, this becomes sigma r square L upon 2 epsilon naught r cube. So this is the value of electric field at a distance which is very far from the disk. So disk, we can just say that it is just like a dipole. That's the major difference. Next question. In this case, we are given, consider a linear quadrupole consisting of two adjacent dipole oriented excuse me please, oriented oppositely and placed end to end. There is effectively a point charge minus 2q at the center. Find the electric field at a distance point, and based on these 2 points, first point is along the axis, second one is along the perpendicular bisector, and the basic figure is given to us. So at the center it is at minus q, so this is our minus 2q. On the left side it will be over plus q, and the right side will be also over plus q. And for the sake of convenience, let us assume that this is our x is equal to 0, left side is our x is equal to minus a, and right side is equal to our x is equal to plus a. And in the a part, we are supposed to find out that field on the axis. And for that, let me redraw the figure here. So we have this plus q, and this is minus 2q, and this is our plus q. And we have taken this equal to x equal to 0, this will be our x equal to minus a, and this equal to x is equal to plus a. And let us take a point somewhere here on the axis, and that point is at a distance r from the origin. And we are supposed to find out electric field at this point P. Therefore, from our one end, this end, the distance will be coming as our r minus a, and from the other end, the distance will be coming as our r plus a. From the origin it is our r. Okay. And so in this case also we are given that the point is distant. Okay. Therefore, if a is the separation between these two charges, and the distance point means the value of r is very much larger than our a. So we have to keep this in mind. So let us solve our part A. Okay, so this figure is for part A. Part A, when the point is on the axis. Therefore, we can write that electric field from each charge at point P, you can say field due to each charge at point P will be equal to, and this we can write as our E of R will be equal to 1 upon 4 pi epsilon naught will be common factor. Okay, we can just algebraically add them, and this will be, first will be Q R minus a whole square minus 2q upon r square plus q, and this comes as our r plus a whole square. Because we have basically 3 independent charges, no doubt dipole is given to us, but in the question it is mentioned that the center one is our connected, so it is behaving like a point charge but having a charge of minus 2q. Okay. So we can take this as a 3 charges. This is first charge having charge of plus q, and this is second charge having a charge of minus 2q, and this is third charge which is also having a plus q. Okay. So we can individually deal with them as a point charges, and therefore now we can just solve it. And for you can say our solution, like I said, we have to keep in mind that value of r is very much greater than value of a. So we are only interested in this factor r, and this is a plus minus a whole square, because we have these two values, so we can just solve it together. And we can take 1 upon r as common, 1 upon r square. It will be coming as 1 minus plus 2a upon r, and that will be plus our 3a square upon r square, plus and so on. So we can simply substitute it, and we get that electric field our on the axis is equal to 1 upon 4 pi epsilon naught q r square, and we have this as 1 minus 2a r plus 3a square upon r square. This will be because of our first part, and we can ignore just higher terms, need not to write them. And then it comes as a plus 1 plus 2a upon r plus 3a square upon r square and minus of 2. And so we can just ignore these square terms, and this r term is going to cancel out. So this will be coming as 1 plus 1, that is 2, and here we have minus 2, so everything goes away. And so we are left with only 1 and 1 upon r cubed. One second, this is our, yeah. So we get the electric field on the axis will be equal to 1 upon 4 pi epsilon naught, and this comes as a 6 q a square, and this will be our 3 plus 3 square, and this will be our r is power 4, okay, because these two terms cancel out. This is 1 plus 1, and this goes by minus 2. So only this term and this term will be left out. Okay, so this is electric field on the axis. Okay. And if you want, you can also find out this by using the dipole also, okay, because these are given as dipoles. But anyways, it doesn't matter how you solve it, okay, because it is specially mentioned in the question that the effective charge at the center is given to us minus 2q. So we simply treat it as a point charge, okay, and find out the electric field because of individually. This is from our plus q, this is from the minus q, minus 2q, and this is for the third charge, that is our plus q, and add them. Okay. Now we come to the field on the perpendicular bisector, that is part B. Field on the perpendicular bisector, and once again we can just draw the figure. So this is our plus q, minus 2q, and plus q, and this is the perpendicular bisector, because here we have taken x equal to 0. This is x equal to minus a, and the right side is x equal to plus a, and this is a distance r which is far away, and therefore this will be equal to our a square plus r square and its square root. Other side also symmetric one, but in this case we can easily see that let us call this as point as our point A. Okay, so let us call this as our A, this is our B, and this is C. Okay, let us call this as point P. So at point P, and this is point our A. So the electric field, because of the charge at A, will be in this direction. Okay, and let us call this as our EA. Similarly, the electric field, because of our C, which is here somewhere, and it will be also in this direction. Let us call this our EC. Magnitude will be same. Okay, it's only the differentiation to make it clear. So we can divide this EA and EC into components, horizontal as well as our vertical. So this will be our EAX and this will be our EAY. Similarly, we are going to get this as our ECX and this will be our ECY. And this ECX and EAX will be same but in opposite direction. So they are going to balance out each other because the distance between everything is same. Okay. And the magnitude is also same. And finally, we are having a charge which is at the center, which is given as minus 2q. And because of this, the electric field will be in this direction and this is our B. So let us call this our EB. So the only electric field will be along our y-axis, net as well as the individual electric field balanced out. Okay. So the x component of both A and C, or we can say the horizontal component, will, we can say, cancel out. So only, and the vertical component of both are going to add, EAY and ECY. Okay. So it means the field will be only in vertical direction. Okay. And if we take upward positive, so downward will be obviously equal to negative. So we can say total field, which is nothing but a vertical only, will be equal to E is equal to 1 upon 4 pi epsilon naught, and this will be over twice E of y. This is twice, let me write it, this will be over EAY plus ECY minus EBY. Now we can just substitute their values. Okay. So we get electric field will be equal to 1 upon 4 pi epsilon naught, and this EAY and ECY magnitude wise is same, so this will be coming as twice Q times R divided by R square plus A square, and this is our 3 by 2, and then we have EBY minus, this is 2Q, and the distance is straightforward the perpendicular distance, that is our R square. Now once again we are going to use, because the value of R is very much greater than our A, therefore we are going to sort out this equation, that is our R upon R square plus A square, and this is our 3 by 2. Sometimes its solution, it's also called as a far field expansion. Okay. So sometimes its expansion is also called as a far field expansion. Far field expansion. And so we can write this will be equal to R, we can take as common, so this will be 1 upon R square, and 1 minus, this will be over 3A square divided by 2R square plus and so on. So we simply substitute in the equation of electric field. So we get our electric field will be equal to and it will be perpendicular electric field, and it will be equal to 1 upon 4 pi epsilon naught, and this is our 2q r square 1 minus 3a square upon 2r square minus 2q upon r square. And this is quite easy to solve, nothing much is typical there. So you can say electric field along the perpendicular bisector will be equal to minus 4 pi epsilon naught, and this comes as 3q a square and r raised to power 4. Obviously the negative signs tell that it will be towards our point B electric field, because from the here also we can say that this charge is our minus 2q, okay, and the distance is our r. So this was quite straightforward, nothing typical was there. Only thing we have to remember that in this case, in the question specifically, it is mentioned that at the center the charge is about minus 2q. So we treat this as a point charge. Okay, so we can use simple our, instead of going into dipole, we simply treat them as 3 independent point charges and sort it out. Okay, if you want to solve using dipole, you can also solve using dipole. Okay, because we already know the relationship between electric field and dipole. I think we did second question based on this. Okay. Next question. We are given a ring of radius r has charge q uniformly distributed on it. It lies in the xy plane with its center at the origin. Find the electric field at all points on the z-axis. For what value of z is the field maximum? Okay. And so we can just draw the figure approximately. So we are given that we have a disk and its center is at the origin, and we have an axis. So axis obviously will be our z-axis because it is lying on xy plane. So we are interested in this point P, and coordinate of this point will be 0, 0, z, okay. And z is this distance, and r is given as a radius of the disk. And in this case we are given that the total charge is q and radius is our r of the ring. It is given to us, but we know that with respect to this point P, in general, whenever we want to solve, so we consider here a small charge element, that is our dq. Okay. And because of this charge element at dq, there will be a symmetric charge element that will be opposite to it. For every point, there will be a symmetric point on the opposite part of it. Okay, suppose we take this, So we take a charge element somewhere here, and it is going to have a symmetric point here. The reason is quite simple for that. So this is our point P, and we have taken a charge element, this, our dq. So because of this charge element dq, it is going to have electric field which direction is this one. Okay. And the symmetric point is somewhere here, and it is also going to have our, you can say, electric field that will be in this direction. Okay. And if we divide these two into components, we can clearly see that, suppose this is our first and this is our second, so this is our E1, so this will be E1 x and this will be E1 y. Similarly, let us put this as E2, so we are going to get this as E2 x as well as our E2 y. In this case, this E2x and E1x are going to cancel out. And this will be true for every symmetric point. Okay, no matter wherever we take the point, because this ring that is given to us lies in xy plane, and the point P is on the z axis. Okay, so it means the point P will be symmetric for each point on the this ring. Therefore, the net electric field, let us suppose it is in z direction, and the z component will be our, you can say, net electric field will be simple, the summation of this E1y plus E2y, and this is true for only 2 points. Similarly, we can generate it for n number of points along the ring. So it means the net electric field and plus and so on will be having a direction along our z-axis. And we already know that the radius is given to us, so this is our r and this is our z. So therefore the distance of this point P, for specifically for if we had taken these 2 points, is our r square plus z square. And this point distance between the point P and any element on this ring will be always equal to r square plus z square. So this will be universally true. Therefore, we can write that our field due to element dq, field due to element dq, and this dq is with respect to point P is at a distance of r, and that distance r is our capital R square and our z square. So this is our distance r. So because of this element dq, we can write the field, that's our dE, will be equal to 1 upon 4 pi epsilon naught charge of the element and our r square plus z square. So we are only interested in our z component. Let us suppose if this angle is our theta, so we can say that our this okay, let me sort it out here. So this is our point P and this is our point 2 and this is our r, and this we have taken as angle theta. Okay, so for this will be our electric field, our E2. So this will be our E2x and this will be our E2y. So this is our 90 degree. Okay, so we can easily find out the angle of it. Okay, so this will be our 90 minus theta. So this will be also 90 minus theta. So we are going to get this will be equal to our theta. Okay, so Ey we can write will be nothing but electric field and its cos of theta. Okay, because this x component will be balanced by the x component of the other part. Okay. Therefore, we can write that our z component, because that will be only left, z component is our dEz will be equal to dE cos of theta, and we already know our dE, and we can also write value of our cos of theta. Therefore, we get this our dEz will be equal to 1 upon 4 pi epsilon naught, and this comes as our z dq, and our denominator will be our r square z square, and this comes as our 3 by 2. Okay. And like I said, we have taken a small element dq, so we can take n number of the small element throughout the ring. So for the total ring, we simply integrate them. So we get our net electric field that will be in z direction will be equal to 1 upon 4 pi epsilon naught, and this is z r square z square 3 by 2 and integration of our dq, and integration of dq will be nothing but the total charge, that is our q. So we can simply substitute it. So this comes as 1 upon 4 pi epsilon naught, and we have this as dq is going to give us a total charge q times z, and this is r square z square and 3 by 2, and direction will be along our z. And we are supposed to find out the maximization of our position of maximum electric field. So we want to find out our position of maximum field, and obviously from the equation we can clearly see that electric field in z direction is proportional to our z, and this is our r square plus z square 3 by 2, because this 1 upon 4 pi epsilon naught is our constant and charge on the ring is also constant. So only variable is our r, and that is z. Okay. So it means we have to maximize this term, this. So we are going to derivate it and differentiate it with respect to z and equate equal to 0. Okay, that's our maximization. So we can say that our dE upon dz, and this comes as our r square plus z square pi by 2, and this is r square minus 2z square. So obviously equal to 0. So from here we can easily write that our numerator will be equal to 0, and this gives us that value of z is equal to r upon square root of 2. Okay, so it means when value of point P rather, this point is at a distance of radius divided by square root of 2, we are going to get the maximum electric field. Next question. It states that find the electric field and charge distribution associated with the following potential. Okay, so please remember here the phi is the representation of the potential, it is not the representation of the flux. So we are given this, basically three regions are given with respect to these three type independent equations. When x is less than 0, our potential is our 0. When x lies between 0 and L, the potential is having some value, and when x is greater than L, potential is having the third value. So this is basically our equation is given to us. So we know that our electric field is our derivative of our potential, negative derivative basically. Okay. So we already know that our electric field where field is the potential is our x direction, so we can say our field in our x direction is our minus d phi upon dx. So we are going to, because this is our, let us suppose region number 1, this is region number 2, and this is region number 3. Normally regions we do some kind of question like we have given two plates with different charge densities, and we have to find out the position. Here we are going to get the net electric field, value of the electric field basically. Same thing, but here it is given with respect to the potential and their respective equations are given. So this is the basic, minor difference there. You can say the approach to solve the question will be same. So we are going to use the basic principle of our relationship between the electric field and our potential, and let us first start with the region 1. And for region 1 we are having x less than 0, and in this case our potential is equal to 0. So obviously the value of electric field will be equal to 0. This is not a big problem. Now we come to our region 2. And region 2 we are given that x lies between our L and greater than 0. And now our potential is given as our rho naught x square and 2 epsilon naught. Okay, so simply we are going to do a derivative of it. So we get electric field will be equal to minus d phi upon dx. Okay. So this gets minus, it comes as our rho naught, this will be 2x and it will be 2 epsilon naught. And this 2 and 2 goes away, so this gives us minus, and we have our rho naught x upon epsilon naught. Okay. And basically from here we can say that the value of electric field is linear with respect to our x and pointing in negative x direction. Only condition is there that value of this rho naught should be equal to it should be positive basically. Okay, therefore we can say that electric field, if this condition is satisfied with respect to this rho naught, it should be mentioned in the question actually, but Ex is our linear in x and pointing in negative x direction. And we come to our region 3. And region 3 is for x greater than L, and the value of our this flux is given as our rho naught L square upon 2 epsilon naught. Now if we look closely between two equations, if we compare rather, so region 2 and region 3, the major difference is that in the region 2 we are having x dependence, and region 3 we are having L dependence. Okay, but the value of our potential should be our x dependent. Therefore we can say that our potential for region 3 is nothing but is equal to constant, because it is independent of x. So our potential will be equal to constant. Okay, and for constant now we can just find out the derivative. So we can say electric field is equal to our negative and d phi upon dx. And please remember once again, here phi is the representation of our potential. It is not the representation of our flux. Okay, please keep this in mind. Okay, last time also I messed it up. I called sometime this phi as a flux and sometime I called this as a potential. But please remember, for the questions which I am trying to solve, the phi is, unless until it is mentioned, the phi will be representation of our potential. It won't be representation of the flux. Okay. So obviously our flux is constant, so our electric field will be equal to 0. Okay. So we have to keep this in mind. Okay. This region 3 was a little bit tricky in the sense that it is dependent upon L, but derivate we are going to do a derivation of with respect to our x. So that's why it will be equal to constant. Now we have to find out the charge distribution, and for charge distribution we have our charge distribution, and for charge distribution we can use the equation that our double derivative of our potential is equal to minus rho upon epsilon naught. Okay. I'm not sure that it is, I don't remember actually. I think it is called as Poisson ratio or Poisson equation. Okay, I have a little bit doubt. I think it's called something like that. And so it's quite simple now, but here only the double derivative will be used. So once again we start with our region 1, and for this region 1 we are given that value of x is equal to less than 0, okay, and the value of potential is equal to 0. Therefore charge distribution is our nothing but rho, which is our charge density. So value of rho will be equal to 0. And for region 2, our x lies between 0 and L, and value of potential that is given to us as our region 2 rho naught x square upon 2 epsilon naught. Rho naught x square upon 2 epsilon naught, and we have to do a double derivative of it. So we are going to get this as our rho naught upon epsilon naught, and this as per our formula will be equal to negative of rho upon epsilon naught. Therefore we get that our rho that is dependent upon x will be equal to minus rho naught. Okay. And finally we are having our x greater than region 3 and region 3 we are having our x greater than L, and like I said here the phi is our constant because it is independent of our x. Therefore its double derivative will be equal to 0, giving us rho is also equal to 0. But here we have to discuss one more case, that is surface charge at the boundary, because our this electric field is discontinuous. Okay, so therefore we have to take care of that our surface charge density with respect to at the boundaries, because the equation is not continuous. Okay, you can just prove it also if you mathematically. Okay. So you can say surface charge at the boundary. Surface charge at the boundaries. And you can say that our field is discontinuous therefore you can write there must be a surface charge density, and we know that our surface charge is equal to our epsilon naught electric field to the right side minus electric field to the left side. Okay. And so let us start for at x equals 0, and our electric field at 0 negative will be equal to 0, and electric field at 0 positive will be also equal to 0. Therefore, we get that our charge density will be equal to 0. Now we come to our x is equal to L. At x equal to L, we can say that electric field at L negative is our minus rho naught L upon epsilon naught. Okay. But electric field at L positive is equal to 0. Okay. And this is negative means our left side, positive means on the right side. And this we can easily you can say differentiate based on the limits. Okay. And we already found out the respective electric field to right side as well as left side. Okay. So when x is equal to less than L, so it will be our this negative, L negative, and x greater than L will be giving us L positive. Okay, like in limits we do. Okay, similarly. And therefore, we can say that our surface charge at the boundary L will be equal to our epsilon naught and the difference between the two, rho naught L upon epsilon naught. Okay. So from here we get rho L is equal to rho naught times L. Okay. So this was important part for our boundary condition. Okay. And next question. It states that a distribution of charge has cylindrical symmetry as a function of distance r from the symmetry axis. The electric potential is, so we are given the potential, electric potential for a cylindrical symmetry, where rho naught is the quantity with the dimensions of a volume charge density. Okay, ideally in every question they should have defined what is rho naught, like defined in this question. Okay, but they are not defined. And so part 2 are there. In part A, find the electric field and charge distribution for all values of r. Part B, from your charge distribution, calculate the total charge per unit length along the cylinder. So here we have to keep in mind that our charge distribution is having a cylindrical symmetry. Okay, so this is the major difference between the previous question and this one. Okay. And so we know the basic formula that our electric field not electric field, but our potential is dependent upon only the distance. Okay. So we know that our potential is dependent only on r. Okay. Therefore, and symmetry cylindrical. Therefore, we can write the basic formula of electric field will be equal to negative of the derivative of our potential with respect to r, and the direction will be our r unit vector. Okay, so this is the minor difference with respect to the cylindrical symmetry. Okay, because potential is only dependent upon the point where it is, we are going to find out the potential. So once again, we are given 3 regions, region 1, this is region 2, and this is our region 3. Okay, once again, phi is the representation of the potential. We have to keep this in mind. Phi here, the phi is not the representation of the flux. Okay. So let us start with region 1. Region 1, we are given that our r is less than equal to capital R. Okay. And our potential is given as 3 rho naught r square upon 4 epsilon naught. Okay, so if you look closely in these three regions, in our potential A should be dependent upon the point where we are going to find out the our potential, which basically means that we have cylindrical symmetry. So this is suppose some kind of cylinder, okay, and here we are going to find out our potential. So this is our r, okay, and capital R is the radius. So in part A, when r is less than our, it means the point lies inside or on the cylinder, our potential is governed by our equation number 1, and in this equation it is independent of this distance where the point lies. So we can say that our phi is not dependent upon our r. So this we can treat it as a constant, because every aspect of this formula is constant. The radius of the cylinder is constant, and the rho naught is mentioned constant, and epsilon naught is constant. Therefore, its derivative d phi upon dr will be equal to 0. So we get that electric field will be equal to 0 when r is less than or equal to capital R. So this is for region number 1. Similarly, we can solve for our region number 2. Region number 2 is given that our r is greater than capital R but less than our 2r. And here the potential is given as our rho naught upon 4 epsilon naught, and this is our 4r square minus r square. So we simply differentiate it. D phi upon dr will be equal to rho naught 4 epsilon naught, and this comes as our, this is our constant 0, so this will be minus 2r. This comes as our 4 goes by 2, therefore this comes as minus rho naught r upon 2 epsilon naught. Okay, and we need to find out the electric field. So electric field we know is the negative of this. So we can say electric field at point R is minus d phi upon dr and r unit vector. So this goes positive rho naught r 2 epsilon naught and our r unit vector. And then we come to region 3, and it will be radially outward because it is coming as positive. And rho naught, if rho naught is positive, it will be coming as positive. So we have a region 3. Region 3 is that our r is greater than or equal to 2r. And here it is straightforward mentioned in 0. So problem is sorted out. So we can say that our potential is equal to 0. Therefore, our d phi upon dr will be also equal to 0, giving us value of electric field is equal to 0. Now we have to find out the charge distribution. Okay. Charge distribution. And for charge distribution, we need to deal with the once again the Poisson's equation, okay, and which states that the potential is equal to 1 upon r. Let me write it. This will be equal to minus rho upon epsilon naught. Okay. And we are given cylindrical symmetry. You can say for cylindrical symmetry, phi is equal to 1 upon r d of dr or d phi upon dr. Okay, so this formula we are going to use. Once again, we are going to take all the three regions. So we have a region number 1. Region number 1, we know that our potential is constant. Okay, we have already proved it. So we get our d phi upon dr will be equal to 0. Therefore, we get this will be equal to 0. Therefore, the charge density will be equal to 0. And now we come to region 2. Region 2, our derivative will be equal to minus rho naught r upon 2 epsilon naught. Okay. And we need to sort out this equation, so we multiply both sides by our r. So we get this as r d phi upon dr, giving us minus rho naught r square upon 2 epsilon naught. Okay. Now we come to this part, and this is d of dr or d phi upon dr. Okay. So basically we are going to find out derivative of this equation. So this comes as our minus rho naught 2r upon 2 epsilon naught. This 2 and 2 cancels out. This comes as minus rho naught r upon epsilon naught. Okay. And this is basically equal to our minus rho upon epsilon naught. Okay, so we can say this is equal to minus rho upon epsilon naught. One second. Okay, I forgot to add here 1 by r. Okay. So this is r and this is also our r, and this r and r is going to cancel out. Now it is correct. Therefore we get from here that our rho is equal to our rho naught. And for region 3. So region 3, we are given potential is equal to 0. So obviously charge density will be equal to 0. That's not much of a problem. Now we have to find out the surface charge densities. Okay, once again we have to look into the discontinuous part. Okay. And so we can say that our electric field is discontinuous at r is equal to capital R and r is equal to 2r. Okay. And once again we have to take care of the boundary condition. Okay. Because of this discontinuity, we can from here say that the surface charges are present. This is almost same as our previous question. There also we dealt with this discontinuity. So surface charge are present. So we can use the boundary condition. And the boundary condition, that is our surface charge is equal to epsilon naught electric field out minus electric field our in. Okay, sometimes we also write it as electric field to the right, electric field to the left. depending upon our, as you feel comfortable. It doesn't have much of the significance. Okay, out and in doesn't mean it can be our left, it can be our right. So our at R is equal to capital R, we already know that our electric field inside will be equal to 0 and electric field on the out is equal to our rho naught R upon 2 epsilon naught. And therefore we can write, we substitute it here, so we get our charge density is equal to our epsilon naught, and this comes as rho naught R upon 2 epsilon naught and minus of 0. And here this epsilon naught goes away, so we get our charge is equal to rho naught R upon 2. So in the previous question we dealt with this using our L negative and L positive. Here we are dealing with this as our out as well as in. We can do as you feel comfortable. And the second discontinuity, we check at the point is our R is equal to twice R, and we are given that electric field in is our rho naught 2R upon 2 epsilon naught, and which comes as our rho naught R upon epsilon naught, 2 and goes away, and electric field out is equal to 0. We simply once again substitute it, we get our charge is equal to epsilon naught, this comes as 0 minus, and we have this as rho naught R upon epsilon naught. This will be coming as epsilon naught cancel out, so this comes as minus rho naught times R. So this is value of our respective this surface charges. Now we come to our part B, which states to find out the total charge per unit length. Okay. Total charge per unit length. Okay. And in particular, for one thing where we are very sure that for all values of this our R greater than 2R, our value of electric field is equal to 0. This we are very much sure of. Okay. So we can simply use for a closed interval, our E dot EA will be equal to 0. So it means the charge total in the enclosed surface will be equal to 0, and charge per unit length is nothing but our charge density, linear charge density rather. So lambda total will be equal to 0. So these were, I think, total 6 questions. Okay, we tried to mix it up by using different types of question, and they were quite not so much lengthy or typical, only we have to take care of our boundary conditions. Okay. And rest were quite easy to solve, not much of problems there. So this completes all the 6 questions for today. Thank you.